So we're going to begin by talking about limits. So as we start into calculus, one of the main things you have to understand is what a limit is, because it's going to lead us to the limit definition of the derivative and then lead us to all the applications of derivatives. So the limit of a function is basically telling you what value the function is going to approach as x approaches a certain number. If you look at our example here, this says the limit as x approaches 2 of this. This right here is our function. So we can call this whole thing f of x. All right, so we're saying that whole thing is the function. And what we're asking is, what is this going to do? What value is it going to approach as x approaches 2? All right. And we can find that out in a number of different ways. We can find it from a graph. We can find it from a table of values. In other words, we could plug in values of x that are closer and closer to 2 on either side and see what happens. Or we can find it by using the method called direct substitution. So we're going to choose 3 different methods. I'm going to show you 3 different methods of evaluating that question. How do you find the limit? But first, we just want to write them down. So we're going to evaluate limits from the graph, and that is only possible if you have the graph of the function. So there are going to be times where you might be given the graph and not the function. You're not told what the function is or what it describes, just you're shown a picture. So then you have to use the graph. And there are other times where you're going to be given the function as an algebraic expression, and you can choose whether you want to draw the graph and then find the limit, or just find the limit using one of these 2 methods. So this method, the graph method, depends on you having the graph. So you can either get that by taking the algebraic expression and graphing it using graphing software of some sort, or you can be given the graph at the beginning, or the other option is to take the algebraic expression and use one of these 2 methods. So let's just look at an example of each of them. So let's say we're going to use the graph. And we typically use the graph when we don't have the equation. If we have the equation, it's easier to just use it and use what we call direct substitution, which we're going to talk about in a minute. But for now, let's say I just gave you the graph that looked like this, the graph of the function that looked like that. And actually, I think I erased part of the function. So let's try to be a little more careful here and get rid of just these, because this is what we're going to get to in a minute. And I can erase this. There we go, and erase this. So let's say I gave you that function. That doesn't look like a typical function that you're used to, probably, because this is a piecewise function. And so it has this break here, this hole, and it has a hole here. And it's actually a hole and a break. So it goes from here down to there. So when we look at this function, right, if we count out our scale and assume that it's 1, so that's 1, 2, so on, and that's back, -1, -2, and so on, then we can ask questions about what is the limit as x approaches certain things. And I'm just going to erase the answers real quick, and then we're going to look at them. So when we try to evaluate the limit at a point, the point is right here. It's going to tell you it's x approaches 2 or -1 or -5. What we do is we go to the graph. So let's take this example first. We're going to try the limit as x approaches 2. So we're going to go up here, and we're going to trace along this function as we get closer to 2. So we're going to kind of come up and say, where is it going as it approaches 2? And you can see that if we count up 1, 2, 3, 4, 5, 6, it's approaching 6 and a bit. Okay, so we're going to say 6.2. All right. And then you have to come from the other side. So we're going to come down towards 2, like so. All right. And you notice it approaches the same value. So we're going to say that's also 6.2. And because it approaches the same value, so it's approaching that number right there, okay, that's kind of the point we're talking about, we can go down here and say the limit as x approaches 2 of f of x, the number that the function is approaching is 6.2. Okay? Now, if we look at -1, that's the next one, and we'll do that maybe in a different color. If we look at -1, we're going to do the exact same thing. So we're going to go to our graph, and first we're going to come along towards -1. Now we're talking about towards -1 on the x, and we're tracing along the function. So we're going to come up like this, and you can see as we come up, it's going to this number. So if we count up, if that's 6, then that's 7, that's 8. So it's approaching 8. All right, now if we come towards it this way, so we're coming towards -1 again in the x, but we're looking at y, it's approaching 6. Okay, it's getting closer to 6. Actually, sorry, that's not 6. That's 5. So we go 1, 2, 3, 4, 5. And we realize then that these numbers are not the same. So this is approaching 8 as we come in from the left, it's called, or from less than the number. And it's approaching 5 as we come in from the right, or bigger than the number. So what we say is, because these numbers are different, because they're not approaching the same thing, we go down here and we say that limit as x approaches -1 does not exist. So we shorten that by DNE, and we say that that doesn't have a value. All right, because it does not approaching the same number. Then if we go to -5, okay, that's the last one, and we'll do that in blue. As we get closer to -5 this way, it's going to 4. And as we come down towards -5 this way, it's approaching the same value. What's interesting about this point is the function doesn't exist. So there isn't an actual value for the function right there, because that hole is there. It's an open circle. But it doesn't matter to us what the function does exactly at -5. What we're asking is, what does it do as it approaches -5? And as it gets close to -5, it's getting closer to 4 in the y. Okay? And so we can write down that this answer is 4. And that's how you evaluate limits from a graph. Now we're going to have time to practice more of that, but that's the concept. So you simply look at the graph and trace along on both sides of whatever the x value is, and you look at the y value, and if they're the same as they were in these two cases, that's your answer. If they're different, then your answer is does not exist. Okay? The second method is by using a table of values. And so what we do with a table of values is we take this number, this x approaches 2, and we say, okay, I want to take some x values that are getting closer to 2. So we're going to take, for example, 1.9, 1.99, 1.999, and we want to get close to 2, like really close to 2. That's why we're going to 3 decimal places. So we're going to do that less than 2. So we're going to go 1.9, 1.99, 1.999. And then we're going to do the same thing above 2. So we're going to get closer to 2, but from above it. So bigger numbers. So 2.1, 2.01, 2.001. And you can kind of see that here. I've written it out here. So we're going to take those numbers to 2.01, 2.001, 2.0001, and 1.9, 1.99, and 1.999. And what we're all going to do is we're just going to take those numbers and actually physically put them into here. Okay, so we're just going to put in 1.9 plus 1 squared, 1.99 plus 1 squared, and so on. And we're going to try, as with any table of values, just going to plug it in, and we're going to see what happens. All right, so I'm just going to block out the second part of this table for a minute, and we're just going to look at, okay, what happens when I put 2.01 in? So what you do, take 2.01, and we'll do it over here just to show you what we're doing. We're going 2.01, we're adding 2, and we're squaring it. So we're getting 4.01 squared, and that comes out to 9.06. Okay, and all we do, and I won't bore you with doing this every time, but all we do is take each of these numbers, okay, and we plug them into that formula just like we were doing, and we end up with our answers. And as we look at these answers, what we try to do is decipher a pattern. So is there a pattern? Is there a number that this appears to be approaching? And if you look at this part here, part that's above 2, you can see that the pattern is that as I add a 0 here, I'm adding a 0 here. So that if I went 2.00001, I would have 9.00006. And what that means is we can make the determination that that's approaching 9, because the more zeros I add, the more zeros there are going to be here. And the same thing happens with these ones. You can notice the pattern again. There's every time I add a 9 here, right? 2 9s to 3 9s went 1 to 2, and then 3 to 4 9s means 2 9s to 3 9s. So I'm adding a 9 every time. So eventually I'm going to have 8.9999 an infinite number of times. And so that's also approaching 9. And because they're approaching the same thing, then I can make the determination that the limit as x approaches 2 of x plus 1 squared is 9. The key thing is that you're picking numbers based on this. Okay, so that's 2. So I picked 3 numbers that were slightly above 2 and 3 numbers that were slightly below 2. If that was minus 2, you would have to do minus these. If that was 3, it would be 2.9999 and 3.0001. So it's important to understand the table of values is a very easy thing to do. It's not a complicated process, but it is important that you pick the right x values. And by right x values, I mean x values that are going to get closer to whatever the number is that you're trying to approach. So that's a table of values. The third method, and this is the method that we use most of the time, we try first if we have an algebraic expression, and it's called direct substitution. And again, mathematicians not very clever with their names or creative with their names, we're simply describing what's going on. So you can imagine direct substitution means that you're going to substitute directly. You're going to take that number and you're going to put it in there and you're going to see what happens. And if it works, that's your answer. If it doesn't work, then we have to do something else. So to use direct substitution, we simply are going to take the 2 and put it in. And when we put in 2 plus 1 and we square it, we get 3 squared, which is 9. And you'll notice we get the same answer that we got from our table values. If we jump back there for a second, we get the same result, 9, but we get it a lot quicker. And so that's the method that we want to use if we can. The table of values is useful, and we will use it, but only after we've tried direct substitution and it doesn't work for some reason. So let's do a few more examples. Let's say, and again, ignore the answer there for a second. Let's say I say the limit as x approaches 0 of x squared plus 3. So this is our function. And what we're going to do with direct substitution is we're just going to take 0 and we're going to put it in. So we're going to go 0 squared plus 3. Now what's 0 squared? Well, that's 0. We're going to add 3. And we're going to end up with an answer of 3. Okay, very simple example. Our answer is 3. And we're done. That's direct substitution.